Hello, welcome. This week we will start our new chapter, chapter 13, buckling of columns. First of all, I want to term buckling. What is the meaning of the buckling? In stack of material, you will see the effects and kind of effects. Maybe you remember that tension and compression. This is the axial effects. Shearing effects is the, you can see in the figure. Also torsion effect and bending effect. And also we measure internal, how we can compute internal effects by using internal forces or moments or internal effects by using these kind of two behaviors, according to these behaviors. Now we will see the new behavior and buckling. Maybe you can easily figure out what is the meaning of the buckling. Is the buckling can occur to compression case when especially in civil engineering structures, the compression forces occurred in columns. Therefore, always we are talking about always the buckling of the columns. The buckling is the sudden change of the shape. You can see, in other words, in the losing the stability of this shape when this structural component under to compression loading. Okay, but the buckling cannot suddenly occur when the compression occurred when the compression force occurred, because there is some kind of the limit force. If the force our force is excess to the limit force, buckling can occur. But if our force is less than to limit force, okay, buckling does not occur. First of all, we try to find this load. Name of this load is the critical load. Critical load is also, you can easily understand my expression. When the members start losing stability, okay, the critical point we call it as the critical load. That I even remember. If our load is greater than the critical load, our structural member could lose stability and buckling can start it. Okay. And also, I don't want to go in detail because I remember that I give a offline video how we can compute the critical load in this case. Okay, and maybe I can just only say one sentence for this. We will use, okay, equilibrium of two structure. That nothing more. Just we are using the equilibrium, and this is a typical small example to how we can compute the critical load. But these also I solved one example and also solution available in here. Also, important term is the buckling critical load of the ideal column. In practical case, we don't have a phase to like these structural shape. Okay, mostly we phase to like these structural shapes. For example, in frames, in trusses. Okay. We are facing to this, like, how we can say, perfectly straight shape. There is no springs some part of this shape. Maybe you can look at or you're around, or there is no spring, there's no additional things on this kind of structure. Therefore, this computation of the critical load of the ideal column for me is extremely important. First of all, I want to say about what is the assumption. First of all, we assume the linear behavior, and also we neglect the small deflection. Did I say what's the meaning of small deflection before? Previous chapters, previous lessons. Did I say what is the meaning of the small deflection theory or small deflection meaning?
I don't think
so. Or
so.
large deflection theory, P delta effect?
I don't think so. You have before mentioned.
Yeah, okay, you remember that. Okay, so I don't want to go in detail. Also, these ideal column definitions, also both ends we assume that's the P ends. Okay, also I say the perfect is straight. Also, there is no eccentricity on this. In other words, P is passed through the centroid of the cross section of this structural member. So I don't want to also go in detail. This is needs a differential equation calculation. Just these equation from chapter 12. You remember that it's second order derivation of this is the y. V meaning that deflection, okay, equals the moment. Maybe you remember that from chapter 12. And also this is equal to minus p times y. How we can compute this relationship? By using take a cross section anywhere of the beam like this. Okay, so I'm taking cross section. I write the equilibrium. For example, on point, I want to make a moment, sigma moment is equal to 0 in this point. I obtain this relationship. This is a kind of the differential equation. After solving a differential equation, I obtain these y formulation. You know there's two integration constants in here, and you know I say both ends are pink by using this relationship. If I want to apply these boundary conditions and I see this term should be 0, then other that by this, if this term should be in 0, C1 cannot be 0, therefore sign equal to 0, and by computational things, and we found P critical. You can see critical force is equal to pi square E times I divided by L square. This is a well-known critical load definition. Always we are asking in the, for example, when the people start to master program in our university and in mechanical department, we are just our first question in the exam is what is the meaning of can you write the formula of the critical load of the ideal column? Also, name of these definition is also Euler-Buckling load. Euler-Buckling load or critical load is two popular definition for this formulation. Also, by using this formulation, also we can compute the critical stress of our structure. And I don't want to pass this part. I think we can solve one example for this. Do you have any question for ideal column or buckling or about this chapter? Is it clear? Did you watch the video about the chapter 13?
Yes.
Yeah. Mm-hmm. So I think I explain more. I explain in detail about how computation, other things like that. Just I want to summarize things. So I hope I could explain well. Okay, this is not complicated things, but when you people see the many formulation, many mathematical operators, then they can afraid about these things. But when you come to the end, I mean the formulation is simple. You are not responsible about the proof, but I want to tell you about how we can obtain, because this is extremely important. Therefore, I am giving to proof in our videos, offline video, and in our slides. But in the exam or in the other things, you are just only responsible about the formulation. Maybe you are wondering that this is the ideal column. This is a pin connection. Hocam, if we have a different connection type, if our formulation will change or not, definitely will change. But in that case, we are using the general case. General cases, you remember that the ideal column is P square I times L square. We put the K term near to L, and K times L square. K is the I can effective length factor. Effective length factor change with respect to the boundary condition. In other words, end condition. If we have a different support types, K terms will change. Also, we have a similar illustration. For example, if both end pins, you know, it's the ideal columns, therefore K is equal to 1. If both ends are free, there is no supports in both ends, K equals to 2. If two ends are fixed, K becomes 0.5. If one end pinned, one end fixed, K becomes 0.7. Also, you know, this is the online exam. Anyone you can find and you can look at you can obtain key values by using these figures. Okay. And also I said about if we calculate the p square also, we can compute the sigma critical, in other words, critical stress value. Okay. And also I think the solution is available in the offline slides. Therefore, solution of the example 12.13.2 it's so important. Therefore, please look at the solutions of this example also. This example is also important. Okay. Please look at the formulation. And also, I want to solve one extra formula for extra example for chapter 13.1, the different example from this. And I think it comes soon. Okay, very well. Oh, this is coming from the previous chapter. Fundamental problems. You will choose. I saw a similar question in the exam like 2 years ago. I remember that. Okay. I saw a similar question again in the exam, or maybe in the homework. I can't remember. I can't solve because these values in this example, the British standards is used. Therefore, I missed that question. British. This is good. 1328, one option. And this one, skip this one. And 1331, the second option. And where is this one? Yeah, and this one too. 1333. Which one do you prefer? 33, 31, and 28. You will choose. I will try to solve one of them. I think it is extremely hard question for you.
31.
Yeah, 31.
31? Okay.
Yeah.
Ladies first. Okay. Therefore, we choose 31. I hope there is no always all the values are numerical. I hope that. Okay, let me read the question. Okay. And the steel bar AB, okay, has a rectangular cross section, and cross section is given here. And A and B is the pin connected, okay. Pin ends determined to maximum allowable intensity W. In other words, distributed load value, load that can be applied BC, causing to AB to buckle. Use the factor of safety 1.5. Factor of safety means that to load divided by capacity should be capacity divided by load should be 105. Okay. Did you hear about the term of the factor of safety in other courses?
Our machine elements course, yeah.
Yeah. This is a typical. Yeah, we can use any type of design. We are using the factor of safety. If you started from the steel design, machine design, and other design types, you heard about this. And let's start writing that. What is our strategy? I think you have no idea. First of all, I want to start from here. You know, AB to buckle. Okay. I know I have a cross section. Okay. I have modulus of elasticity. Okay. Also, I have yield modulus. I will explain why I need. Okay. Also, I can measure to capacity of this column. After that, I want to the buckling capacity and this W force. After that, we can easily obtain W force. Okay, do you understand what I mean? Anlamadınız. You don't understand. Oh, sunrises come to my whiteboard. I think I need to close my curtains. Is it dark or good? What do you think? Is it enough to see? Can you see the whiteboard clearly?
It's fine. It's fine. Yeah.
Yeah, there it is. So, first of all, I want to redraw as like this shape, like this. There's my black color, and we have a distributed force in here. Okay. Okay. And here is the pin support. Therefore, I have two reaction in here. Okay. So also here is the pin support in here. I can write CY, CX. We don't need to calculate this, but I'm writing this part. Okay.
And again, we can see board.
Sorry?
We can see your board.
Sorry. Sorry, Buse. I can draw, but for myself. Now you can see. This is the R shape, but this not seems to be exact three-way diagram. Okay, do you understand this one? See?
Yes.
Yeah, okay. Is it enough to explain to our solving? Unfortunately, because I need to cut our structure from this point. If we cut this point, okay, you can see there's both ends are pin. In other words, when both ends are pin, this bar can resist only to axial load because it seems to be like truss member. There's no shear and there's no moment occur in this element because point A, point B, and point A are pin. Okay, maybe you can remember from the static course. Do you remember? If you don't remember, I can remind you. Okay, therefore, if I cut this system, I have two systems. I can part the first part. This part, the first part is the beam part. The second part is the column part. Do you understand this definition? If you don't understand, you can ask questions. I cut system from point B. Okay, when you cut this system, I have first of all one element, column element, and column element can resist only to axial load because this element is torus element. Therefore, there's only vertical force exposes to this P, therefore 1 unknown, 2 unknown, 3 unknown. Can we find to this P value? Can I find? Bulabilir miyim? Okay, no one
Yes,
can
we can find.
Like sigma FC is equal to 0. Okay, you know, there's a omega value of load. What is the length? 5 meters. Therefore, it's 5 omega. And this dimension is 2.5. So, and my assumption counterclockwise is positive. I want to take. And after that, I want to continue. Let's start from the P. P times 5. In other words, 5P. Okay. And minus, because this rotates to, I'm sorry, this is minus now. This is rotates to clockwise direction. This is rotates to counterclockwise. 5 omega times 2.5. What is the value? And 12.5, isn't it? 5 çarpı 2, 10, yarısı. 12.5 omega is equal to 0. Then it's, I'm sorry, we should be positive. So P is equal to 2.5 omega. Okay? So this value is equal to 2.5 omega, 2.5 omega. Do you have any question up to now?
No question.
No question.
Okay, very well. So my column, like this shape, the first value is, this is 2.5 omega, 2.5 omega. This value should be lower than P critical. Okay. So first of all, I want to compute to P critical. First of all, how we can, do you remember the formulation of the P critical? Pi square E
E
times
times I over R square.
R square. Okay. So L is given 3 meter. We know this. Also modules of elasticity given. Where is this one? 200 gigapascal or megapascal. I can't see the completely. I think 2,000 yes, 2,000 gigapascal. Okay. And also, sorry, I need to be a little bit more like this. Okay. So just only we don't know the moment of inertia. How we can compute the moment of inertia? We have a cross section. Okay. So we have and I'm sorry, 20 millimeter and 30. So we can compute, this is the, for example, this is X direction, this is Y direction. So we can compute Ix, Iy. So I write formulation is I is equal to Ix or Iy. Which one? Do you have any idea? Just shooting, say something. Say Ix, Iy. Okay, no one wants to respond. Okay, I is equal to, like, minimum Ix, Iy. You understand? because the system can buckle to weakness point. Just I want to show.
Hocam.
Dondu yine ama.
Dondu mu?
Evet.
Şu an geldi mi görüntü?
Görüntünüz tamamen dondu. Cross section'ı çizerken dondu.
Bir saniye. Bir çıkıp geleyim mi? Şey olarak. Siz durun sistemden. Ben bir en güzeli o. Çıkıyorum, geliyorum. Şöyle bir çıkıp leave yapayım. Leave meeting yok mu orada? İnşallah böyle kapatınca siz gitmezsiniz. Okay. Şu an gelmedi değil mi görüntü?
Gelmedi.
Görüntüyü kapattım.
Gözüküyor hocam şu anda.
Okay, very well. Let's continue. So we have, I'm taking two, not IX, IY. I am taking one of them. Just which one is the minimum? I'm computing to this one because if we are taking two, we critical the minimum value. The weakness point, we are measuring the weakness point. You know, this is the traditional thing, and in design problems, always we are considering two most critical cases, the weakness case. Therefore, which one is the minimum, IX or I1? You can easily say, you know, the formulation of the I is equal to B times H cubed divided by 12. So H is, which in case the H is for IX. So you know IY is equal to B cubed times H divided by 12. So I think IY is much more smaller than IX because H is greater than B. Can you see this? Is it true? Do you agree with me?
Yes.
So I is IY and also is equal to B times B 23 2 times 30 divided by 12. I need a calculator. Sorry, like this. Yes. Does it equal to İnşallah is it true? It's equal to 20 times 10 to the power 3 millimeter power 4. Okay. This is our cross section. And also, you know, in general case, we are using the K times L squared. You know, if both ends are thin, K equal to 1. In other words, this is the ideal column. For example, in the exam, you can write the general formulation and you can say K is equal to 1. Maybe you can say, hocam, this is the ideal column. I don't need to write the K. I can just only write the L square. Both strategies, both ways are correct for me in the exam. Which formulation do you want? You can use like this question. Okay. Let's try to write the values. I am working to Newton millimeter terms. Therefore, Newton divided by millimeter is gigapascal. Do you remember? Newton divided by millimeter square is gigapascal. So P square times 200 times 20 times 10 to the power 3 divided by L is 3 meter. So I write 3,000 square. Okay. After that, I found that calculated. Take me a few seconds to compute. P square times 200 times 20 power 3 divided by 3000 square. Hopefully it is correct. Yes. This equal to, I'm sorry, that's gigapascal, meaning that, not Newton millimeters. Newton millimeters, sorry. Newton divided by millimeter square is megapascal. Okay, let me like Newton meter square is Pascal, kilonewton meter square is kilopascal, like Newton millimeter square is megapascal, kilonewton millimeter square is gigapascal. After reminding for myself, sorry, I write in here. Okay. Just remind for myself, okay, not for you. These things. Okay. So after that, I compute that. There's my solution. 4.39 kilonewton because I'm working these units. Let me control. Okay. So this value is enough or not in our example, unfortunately, because this is from the buckling. Okay. Also, I want to consider to this term. Also, we are considering the, and we remember to. I want to open to this slide. Okay. When in the column design, okay, we are not only buckling, also we have to consider in the compression case. Okay. In compression case, we have to measure the critical yielding stress. Maybe you remember that from chapter 2 or 3, I think that. I can't remember the exact chapter. Do you remember to compression check? Maybe in chapter 11 we did it. Okay, so it is easy. So, you know, in stress over than sigma yielding R case, stress in compression is equal to P times, this is the P critical one, I can say, this is the P critical Q, right, divided by area is equal to yield stress. Yield stress is equal to value, I need to again open to in example. This is the megapascal. Can I convert to the gigapascal? Do you want this? I think I need to convert. So I need to write to 0.36 gigapascal. So area is, we have a cross section, 20 times 30. So our second P critical is equal to 0.36 times 20 times this, I can write that 20 times 30. This is equal to, you can see, P critical 2 is equal to 216 kilo. So I have two critical force. What do you think? Which one I need to take? The first one or second one? P critical 1 or P critical 2?
I think first one.
Remember, the first one. Why? Because this is smaller, isn't it?
Yes.
I should take the smallest one. The smallest one is this one. Therefore, P critical is minimum P critical 1, 2, and therefore P critical is 4.39. Okay. Can I erase this part? I want to continue here. Like this. So I found P critical is equal to 4.3, and also this should be, we can remember that, 2.5 omega critical or omega. So after that, we can easily find omega. Omega is equal to 1.35 kilonewton meter. So our result is this. Do you have any question? Maybe you ask, Hocam, in here we are using the millimeter. Why we are using in here meter? You remember that when I completing to relationship P and omega, I use the metric units. Therefore, I have to write the metric units. But when I completing to P critical, I use the millimeter. Okay. If you confuse, okay, you can use also millimeter in here, or you can use meter in here. Which one do you prefer? It's up to you. Do you understand? Do you have any question?
No question.
No question.
Okay. I solved many examples in chapter 30. I remember that more than 5 or 10 5 example. I think that yes, 5 example. Also additional, I solved 1 example in here. I think this example is enough for this week. Okay, next week I am planning to solve 1 more example for chapter 30. Then we will pass to do our last chapter, chapter 40. If you have no question, we can finish our course. Muhammed, Buse, Berka, Berke, Umut, do you have any question?
No question. Thank you.
Thank you, sir.
I have a question, so thank you.
Thank you very much for your attendance, for your interest, and for your attention. Okay. See you on next week. If you have any personal question, do not hesitate. You can anytime you can ask on classroom or as an email. Okay. Just also I want to remind that. Okay. See you next week.
See you.
Oh, also. Bye bye.